March 24, 1941, Quonset Point, Rhode Island. In the early spring of 1941, at the Naval Air Station in Quonset Point, engineers from the George A. Fuller Company gathered around a table covered in drawings and calculations. The United States Navy had delivered a daunting directive: create a transportable structure that could be erected by inexperienced troops using nothing more than basic hand tools in hostile territory. The deadline was brutally short, less than 2 months. The new design had to surpass the durability of anything fielded during the previous war and be ready before summer arrived. Across the Atlantic, Britain already had a solution that had served for a quarter of a century: the Nissen hut. Under ordinary circumstances, 6 trained men could assemble one in roughly 4 hours on a prepared concrete slab. In ideal conditions, a well-practiced Royal Engineers team had reduced that time to just under 90 minutes. Yet for American planners, that was not sufficient. They sought a structure that could be built faster, by less specialized crews, and with greater efficiency. What was emerging in the United States was not merely a new building, but a new philosophy. One that valued speed, standardization, and simplicity over inherited practice. The contrast between the British hut and the American version that would follow was not primarily about size or weight. It reflected 2 distinct industrial mindsets. American designers were prepared to strip a structure down to its most essential components so that any soldier armed with a hammer could assemble shelter as readily as he handled a rifle. This shift would ultimately reshape military construction during the war. Needed accommodation for enormous numbers of newly mobilized soldiers, and conventional construction could not keep up with demand. Nissen, born in Canada and trained as a mining engineer, found inspiration in an unexpected place: a semi-cylindrical drill hole roof at Queen's University in Kingston, Ontario, which had collapsed 2 decades earlier. He recognized that a half-cylinder form could deflect shrapnel more effectively than box-like buildings, whose right-angled corners were structurally vulnerable. Within 3 days in April 1916, Nissen completed 3 prototype huts. Fellow officers evaluated the models, and after revisions and approval, the design was officially adopted later that summer. Structure and assembly. The hut's design combined simplicity with practicality. Its outer shell consisted of curved sheets of corrugated steel attached to T-shaped steel ribs spaced 6 feet apart. These ribs were secured to horizontal floor supports at both ends. Wooden strips ran along the length of the structure, providing fastening points for the steel panels. 3 standard widths were available: 16, 24, and 30 feet, while the length could be extended in 6-foot increments. A common configuration measured 16 feet across and 36 feet long. The corrugated steel panels overlapped at the ends and sides to improve weather resistance, and dozens of sheets were required for a single structure. Interiors could be lined with additional panels or wooden boards, leaving a gap that provided limited insulation. Each end was framed in wood and fitted with doors and windows. Construction began with a prepared concrete base. Workers bolted the steel ribs into position, attached the wooden members, and secured the metal cladding. Tension wires had to be tightened along each rib to prevent the structure from spreading under load. When disassembled, the components could be transported in a standard 3-ton military wagon. By the end of the First World War, production had reached at least 100,000 units. Nissen himself was promoted to lieutenant colonel, awarded the Distinguished Service Order, and secured patents in multiple countries. Notably, he relinquished royalty claims for the duration of wartime production, a policy his company repeated during the Second World War. Life inside and interwar use. Despite their practicality, Nissen huts were far from comfortable. In Britain's cold climate, occupants complained of drafts and poor insulation. In hotter regions such as the Middle East and the Pacific, the metal shells trapped heat and humidity. Early versions often had bare earth floors, lacked electricity, and relied on small stoves for warmth. Even so, they offered clear advantages over tents: durability, reusability, and greater protection from the elements and enemy fire. Although demand declined during the interwar years, the outbreak of war in 1939 brought renewed production. Yet by 1941, the United States was preparing to advance the concept further, transforming a useful wartime expedient into a symbol of industrial efficiency and rapid deployment. Parallel concepts to the British Nissen hut appeared in several countries during the early 20th century. In Britain, the Romney hut followed a similar path, and in the United States, the idea would eventually evolve into what became known as the Quonset hut. For years, the Nissen design remained the benchmark, until a group of American engineers began questioning one core assumption. Did the structure really need an internal skeletal frame at all? And typhoons, and simple enough for untrained personnel to assemble using basic hand tools. The Fuller Company was no stranger to ambitious projects. It had previously constructed major American landmarks, such as the Flatiron Building in New York and the Lincoln Memorial in Washington, D.C. At the time of the Navy's request, the firm was already under contract to build facilities at the Quonset Point Naval Air Station in Rhode Island. Now, its design team, led by architect Otto Brandenberger and engineers Robert McDonald, Tomasino Secondino, and Dominic Ergo, was handed a formidable challenge. Conceive an entirely new prefabricated shelter, establish a factory to produce it, and deliver the first units within just 60 days. As a starting reference, the Navy supplied plans for the British Nissen hut. The Fuller team carefully analyzed the design. They appreciated its aerodynamic half-cylinder form and the resilience of its corrugated steel shell. However, they also recognized a key drawback. The Nissen relied on a network of internal steel ribs connected by bolts, a system that complicated assembly and slowed construction in the field. Rather than discard the curved profile, the American engineers decided to rethink the structural method itself. Their strategy was to shift complexity away from the job site and into the manufacturing process. By simplifying field assembly, they aimed to reduce construction time dramatically. In an extraordinary display of wartime urgency, the Fuller Company erected a large production facility near Davisville, Rhode Island, in just 30 days. But the American version introduced a critical refinement. Each rib was formed by welding two specially shaped steel channels back to back, creating a continuous serpentine groove along its length. Viewed from the end, the groove resembled an elongated W. This subtle innovation transformed the assembly process. Instead of drilling holes and fastening panels with bolts, workers could hammer nails directly through the corrugated steel exterior and interior lining into the grooved ribs. The W-shaped channel gripped nails with remarkable strength, often more securely than wood. This eliminated much of the labor traditionally required for metal fasteners. The outer shell consisted of curved, galvanized, corrugated steel panels produced by the Anderson Sheet Metal Company of Providence, Rhode Island. which engineered custom equipment to achieve the precise curvature. Inside, pressed wood panels made of masonite formed the interior walls. A layer of paper insulation sandwiched between the steel exterior and the inner lining provided significantly better thermal performance than the simple air gap found in Nissen huts. Flooring consisted of 1-inch tongue-and-groove plywood mounted on a raised metal base. The ends were enclosed with prefabricated plywood sections containing doors and windows. Depending on site conditions, the structure could be set on concrete slabs, pilings, or directly on prepared ground. Each unit cost approximately $800 to manufacture, roughly equivalent to $12,000 today. Grooves. In June 1941, the first Quonset huts were sent overseas to Britain under the Lend-Lease program. Ironically, the country that had pioneered the Nissen hut a quarter-century earlier now received a shelter that was quicker to erect and more comfortable to occupy. By the end of 1941, approximately 8,000 T-rib units had been manufactured. Field performance soon validated the design. Reports from Iceland described a violent storm that tore coverings from numerous British Nissen huts and severely damaged aircraft along the shore. The Quonset huts, by contrast, remained largely intact. The attack on Pearl Harbor on December 7, 1941, marked a turning point. With the United States fully engaged in World War II, demand surged immediately. The U.S. Army placed an order for 16,000 huts, and requirements escalated rapidly as military operations expanded across multiple continents. Despite its success, the T-rib model revealed practical limitations. Because the curved walls extended all the way to the ground, usable floor space along the edges was restricted. Beds, equipment, and utilities had to be positioned inward, reducing efficiency. Additionally, military planners sought even faster assembly times and lighter shipping weights. In response, the Fuller Company introduced a redesigned model featuring 4-foot vertical sidewalls supporting a modified arch. This adjustment significantly increased functional interior space. Roughly 25,000 of the revised huts were produced at the naval facilities in West Davisville. Yet a private firm, Stran-Steel Corporation, already active in the lightweight steel housing market, recognized room for further refinement. The company had previously presented its steel residential framing system at the Century of Progress International Exposition within the Homes of Tomorrow exhibit. Building on that experience, Stran-Steel engineers proposed taking over production and applying their own streamlined manufacturing strategy. In September 1941, the U.S. Navy granted the firm a contract to manufacture the Quonset hut. Formal design approval followed the next month, and over the course of the following year, Stran-Steel gradually became the principal producer. When operations at Quonset Point were wound down in 1943, the company had firmly established itself as the leading manufacturer. Although Otto Brandenburger continued to supervise the project, the hut's structure was substantially re-engineered. The updated version returned to a true semicircular arch. While this reduced usable interior floor area slightly, it significantly improved both portability and production speed. The most consequential change involved the steel ribs. The earlier T-shaped members were eliminated. In their place, engineers joined 2 thin steel channels back-to-back, creating an I-shaped structural element. A continuous groove ran between the paired channels, allowing assembly with friction-driven nails rather than bolts. Cargo volume. Flooring was upgraded from 1-inch planks to half-inch plywood. Thinner galvanized steel replaced the heavier exterior panels previously used. The cladding system was redesigned so that only the ridge required factory curved sheets. The remaining panels were flat and installed horizontally, allowing them to be transported efficiently in stacked bundles. A fully crated Stran-Steel hut required between 270 and 325 cubic feet of shipping space, substantially less than the 450 cubic feet needed for the earlier redesign, and even less than many canvas tents mounted on wooden frames. Assembly procedures reflected the same philosophy of simplification. Crews first laid out the floor frame and secured the plywood decking. Rib sections were belted together on the ground, then raised and fastened to the base at 6-foot intervals. Nailing strips were added between ribs, followed by corrugated steel panels installed from the ridge downward. Interior masonite lining was attached directly to the framing. Prefabricated end walls, doors, windows, and partitions were then installed, along with heating or ventilation equipment if necessary. A team of 10 men, equipped with basic hand tools, hammers, and wrenches, could erect the entire structure in a single 8-hour shift. No cranes, welding gear, or specialized trades were required. Soldiers simply followed printed instructions and drove nails into the grooved steel members. Industrial production methods reinforced this efficiency. At the Great Lakes Steel Corporation plant in Detroit, multiple assembly lines operated simultaneously. Steel coils arrived by rail and were stamped into channels using progressive dies. After cutting to length, the channels were paired and tack-welded to form rib sections. Splice plates and bolt holes were added with precision. Every element was engineered for interchangeability and error-resistant assembly. In contrast, the British Nissen hut demanded a higher level of craftsmanship. Its ribs required numerous bolted joints. Corrugated sheets had to be positioned carefully and fastened with hook bolts, and tension wires needed precise adjustment to prevent structural spread. Weather often complicated the work. Rain reduced grip on steel surfaces, and cold temperatures hindered manual dexterity. Successful assembly depended heavily on experienced crews and favorable conditions. The American hut proved far more tolerant. Nails could be driven in nearly any climate. The grooved ribs naturally guided panel alignment. The eye-shaped members offered greater inherent stiffness than T-sections, minimizing the need for additional bracing. Even an inexperienced team might complete the structure in 12 hours instead of 8, but completion was almost guaranteed. The underlying distinction reflected two engineering cultures. British practice focused on technical precision supported by skilled labor. American practice prioritized designs that minimized reliance on expertise and maximized scalability. By 1943, the contrast was measurable. Under ideal conditions, a Nissen hut could be assembled by 6 trained men in 4 hours. A Quonset hut required 10 men and roughly 8 hours, but demanded no prior experience. While on paper assembling a Quonset hut might appear slower than a Nissen hut, the practical reality was different. Predictable. Additionally, Quonset huts demanded less experienced oversight. A sergeant with basic literacy could supervise using printed guides, whereas Nissen huts required at least one crew member familiar with structural mechanics and tensioning methods. This distinction proved vital for a rapidly growing military with large numbers of inexperienced recruits. Production numbers highlight the scale of the difference. During World War II, Britain produced roughly 100,000 additional Nissen huts beyond World War I totals, while the United States manufactured between 150,000 and 170,000 Quonset huts from 1941 to 1945, including all variations like warehouse models. U.S. output exceeded British totals despite starting a quarter-century later and simultaneously producing ships, tanks, and aircraft. Quonset huts were deployed wherever American forces operated, serving as barracks in Iceland and the Aleutians, hospitals in North Africa and Italy, offices and storage facilities in England, and housing across Pacific Islands from Hawaii to Okinawa. The Navy approved 86 official uses for Quonset structures, ranging from barracks and chapels to bakeries, medical offices, mess halls, and repair shops. The largest Quonset ever built was a 54,000-square-foot warehouse on Guam, using rectilinear steel frames with arched roof sections that could expand horizontally, representing a significant development from standard designs. More common were the 40 by 100-foot elephant huts and smaller 20 by 48-foot Quonset 20 models, which became the most frequently used variant, providing open, clear-span interiors suitable for aircraft maintenance and supply storage. In the Pacific Theater, the advantages of Quonset huts were most evident. U.S. Navy construction battalions, the CBs, mastered quick assembly. They could unload, transport, prepare foundations, and erect multiple huts in a single day. Foundations were adapted to local conditions, slabs poured directly on coral, wooden pilings or steel supports for weak soil, and additional anchoring in typhoon-prone areas. At Tinian, CBs built an entire airbase with dozens of Quonset huts in weeks, supporting B-29 operations, including the aircraft that carried the atomic bombs over Japan. Similarly, at Guadalcanal, crews constructed functional complexes under intermittent artillery fire and air raids, providing troops with organized, electrically powered, and weather-protected facilities, while the Japanese relied on improvised shelters. British forces continued to rely on Nissen huts, particularly in North Africa and Europe, where skilled Royal Engineers oversaw construction. A 4-hour assembly for 6 men remained acceptable, but was slow compared with the speed and flexibility offered by Quonset huts. When American troops arrived in late 1942 with Quonset structures, British commanders observed the rapid creation of fully equipped bases with interest. The Germans, focusing on weapon and vehicle production and giving prefabricated housing low priority, were struck by the scale of U.S. construction capabilities. Photographs and intelligence reports from 1943 onward showed Quonset complexes appearing across the Pacific, North Africa, and England, revealing the astonishing ability of the United States to mass-produce prefabricated buildings while simultaneously maintaining a vast war production effort. The Quonset's success lay in its simplicity, standardization, and adaptability. Itself part of an expansive industrial network, the manufacturing strategies applied to Quonset huts mirrored those used in producing Liberty ships, aircraft components, and tank parts. Principles such as standardization, prefabrication, assembly line construction, and interchangeable parts were central to American wartime production. While the Quonset hut demonstrated these methods effectively, it was only one example among many. After World War II ended in 1945, the future of these practical military structures was uncertain. The answer arrived in the form of an urgent housing crisis. Nationwide, the government estimated a need for 3.5 million new homes in 1946 alone, driven by returning servicemen and pent-up demand from the war years. To address this shortage, the War Assets Administration began selling surplus Quonset huts at locations such as Port Hueneme, California. On the first day of sales, 75% of 811 available huts were purchased by 600 veterans, and similar transactions quickly took place across the country. Prices for the huts ranged from $295 to $1,000, depending on size and condition, making them far cheaper than conventional construction. However, moving a Quonset presented logistical challenges. Each unit weighed around 6 tons when disassembled. Transport by rail cost 32 cents per 100 pounds, though groups of 6 veterans could combine resources for a discounted 10.5 cents per 100 pounds. Many opted to hire trucks, resulting in an unusual spectacle on highways nationwide. The University of Iowa established Quonset Park, a community of these curved steel structures, while Yale continued to use them into the 1960s. In Los Angeles, Roger Young Village emerged as a Quonset-based residential community for veterans and their families. Named after a Medal of Honor recipient killed in the Solomon Islands, the village, located near Griffith Park, eventually accommodated roughly 1,500 families in 750 huts. Residents built a sense of community through local organizations, sports leagues, dances, and on-site schools. Yet they understood the temporary nature of the housing. As veterans gained employment and savings, they gradually moved to conventional homes. By the mid-1950s, Roger Young Village was largely vacated and redeveloped. Surplus Quonset huts found new roles in agriculture and small business. Farmers used them for equipment storage, hay barns, and livestock shelters, while entrepreneurs converted them into workshops, warehouses, and retail spaces. Notably, brothers Owen and Harold Bradley installed a hut as a recording studio in Nashville in 1954, simply called the Quonset Hut. Its curved steel shell produced excellent acoustics, contributing to the Nashville sound. Iconic recordings by Patsy Cline, Conway Twitty, Loretta Lynn, and Johnny Cash were made there. The studio was later purchased by Columbia Records in 1962 and operated as Studio B. Despite these adaptations, Quonset huts gradually declined as family homes. Veterans often associated the curved walls with military life, and the 960-square-foot interior of the standard Quonset 20, constrained by sloped sides, was insufficient for post-war families. Quonset huts remain scattered across the United States, a testament to wartime over-engineering. In contrast, British Nissen huts followed a slightly different path after the war. Many were repurposed for industrial or agricultural uses, while thousands provided temporary housing for post-war migrants in Britain, Australia, New Zealand, and other Commonwealth nations. In Belmont, New South Wales, for instance, 50 Nissen huts were adapted as private residences, illustrating a global legacy of military prefabrication repurposed for civilian life. During World War II, Australia became home to a distinctive type of residential structure. Over the decades, 17 of these huts were torn down, but 33 have been renovated and are still in use today. In the United Kingdom, a few Nissen huts remain scattered across former military sites, now repurposed as workshops, storage facilities, or museum displays. The Chiltern Open Air Museum, for example, presents a World War II-era Nissen hut, complete with an authentic Royal Air Force briefing room. Some of these structures have even been adapted for commercial purposes, showcasing the practical longevity of wartime design. The differences between the Quonset hut and the Nissen hut reveal broader contrasts in American and British engineering philosophies. British designs focused on elegance and efficiency during production. Nissen huts required relatively few parts, with T-shaped ribs and corrugated panels that were easy to manufacture, assuming skilled crews would handle assembly. American design, in contrast, prioritized simplicity for the end user. Incorporating strand steel made production more complicated, creating grooved ribs that were harder to fabricate than plain sections, but this complexity translated into ease in the field. The M1 Garand rifle, though harder to produce than the British Lee Enfield, was simpler for soldiers to maintain. American tanks featured straightforward transmissions that could be repaired by any mechanic, while German tanks were sophisticated but maintenance-heavy. American Liberty ships used standardized parts and assembly line techniques, allowing production rates of 3 ships per day at their peak. The goal was speed of deployment and mass production, rather than refinement of individual units or elegance of design. The scale of American Quonset hut production illustrates this philosophy. Between 150,000 and 170,000 huts were built in just 4 years. Using a midpoint of 160,000 huts, production averaged roughly 308 huts per week, 44 per day, or nearly 2 per hour, around the clock. No traditional construction method or individual craftsman could have matched such output. Modern prefabricated building techniques owe much to the Quonset hut concept. By shifting complexity from the field to the factory, structures could be assembled with minimal skill. Innovations like grooved ribs are echoed in modern steel framing and prefabricated wall panels, which rely on smart design to reduce labor requirements. Today, Quonset-style structures are still in use worldwide. Adapted with 21st-century materials such as galvanized steel and advanced anti-corrosion coatings. Engineered versions can withstand extreme weather, including Category 4 hurricanes and heavy snow. The semicircular shape provides inherent strength, and components ship efficiently. In Alaska, where thousands of original World War II Quonset huts remain, local regulations sometimes limit new construction to prevent overconcentration. Correctly, American engineers designed huts so straightforward that errors were nearly impossible, even by untrained workers. In the context of total war, requiring millions of civilians to mobilize rapidly, the American approach proved decisive. The difference between building a hut in 4 hours versus 8 multiplied across thousands of sites on 6 continents and represented a significant conservation of labor and time. A 10-person crew could erect a Quonset hut in a single day, a revolutionary concept in military construction that exemplified American industrial philosophy and contributed to Allied victory in ways often overlooked. British Nissen huts were impressive for their time, with 6 men able to complete one in 4 hours in 1916. By 1941, however, total war demanded large-scale, easily deployable solutions. The Quonset hut met this need with elegant simplicity, a structure anyone could assemble. Today, curved metal buildings for small businesses, storage, or agriculture trace their lineage to this innovation. The Quonset hut demonstrated that true breakthroughs do not always require complex technology or exotic materials. Sometimes they emerge from asking a different question, not how to build something better, but how to make it so simple that anyone can build it. In the end, America's industrial edge in World War II was not only in producing vast quantities of tanks, aircraft, and ships, but in designing every system and structure for mass production and easy field deployment. The Quonset hut, completed by 10 men in a day with nothing more than hammers, perfectly embodied that philosophy: effective, scalable, and transformative.